Yes, a ground wire is required for any underground electrical distribution system to provide a low resistance path for fault current and to maintain a uniform potential gradient in the ground. It also protects against voltage surges and lightning strikes. No, a bonding wire is not typically required for underground feeder services. Yes, a ground wire is required to provide a low resistance path for fault current and to ensure proper equipment grounding. It also provides a reference point for voltage measurements and protects against overvoltages. Yes, a bonding wire is required to electrically connect all metal parts of the electrical system, including the conduit, enclosures, and equipment. This ensures that all components are at the same potential and prevents the accumulation of static charge. To learn more about this in detail, firstly, the National Electrical Code, specifically Section 250.0, provides detailed requirements for grounding and bonding in electrical systems. Secondly, UGLI's Electrical References, which is a comprehensive reference book that covers electrical systems, including grounding and bonding. Thirdly, Practical Electrical Wiring, a practical guide to electrical wiring practices, including grounding and bonding techniques. Fourthly, Electrical Grounding and Bonding, a specialized book that covers the principles and applications of grounding and bonding in electrical systems. Fifthly, Electric Power Distribution Handbook, a comprehensive reference on electric power distribution systems, including grounding and bonding requirements. Let's delve further into the specifics of grounding and bonding in electrical systems. Grounding, in essence, is the intentional connection of a neutral conductor or equipment enclosure to the earth. This connection establishes a low impedance path for fault currents to return to the source, thereby facilitating the rapid operation of overcurrent protection devices like circuit breakers or fuses. The primary purpose of grounding is to minimize the risk of electrical shock to personnel and to prevent damage to equipment during fault conditions. Bonding, on the other hand, involves connecting together all metal parts of an electrical system that are not intended to carry current. This includes items like metal conduits, equipment enclosures, and even metal water pipes that might be in proximity to electrical equipment. The objective of bonding is to create an equipotential plane, ensuring that all metal parts are at the same electrical potential. This prevents voltage differences from developing between different metal components, which could lead to dangerous touch potentials during a fault. The National Electrical Code, or NEC, is the cornerstone of electrical safety standards in the United States. Section 250.0 of the NEC is entirely dedicated to grounding and bonding requirements. It provides detailed rules and guidelines for the proper installation of grounding and bonding systems in various types of electrical installations, including residential, commercial, and industrial settings. The NEC outlines specific requirements for the size and type of grounding and bonding conductors, as well as the methods for connecting them to the grounding electrode system. It also addresses the grounding of specific types of equipment, such as transformers, generators, and motors. UGLI's Electrical References is a widely used pocket-sized handbook that serves as a quick reference guide for electricians and electrical engineers. It contains a wealth of information on various electrical topics, including grounding and bonding. UGLI's provides concise explanations of grounding and bonding principles, along with practical examples and illustrations. It also includes tables and charts that are useful for selecting the appropriate size of grounding and bonding conductors for different applications. Practical Electrical Wiring is a comprehensive textbook that covers all aspects of electrical wiring, from basic principles to advanced techniques. It includes detailed chapters on grounding and bonding, explaining the theory behind these practices and providing step-by-step instructions for proper installation. Practical Electrical Wiring emphasizes the importance of following the NEC requirements for grounding and bonding and provides guidance on how to comply with these requirements in different situations. The Electrical Grounding and Bonding is a specialized book that focuses exclusively on the topic of grounding and bonding. It delves into the theoretical underpinnings of these practices and explores the various methods and techniques used to achieve effective grounding and bonding. Electrical grounding and bonding covers a wide range of topics, including grounding electrode systems, equipment grounding conductors, bonding jumpers, and surge protection. It also addresses the grounding and bonding requirements for specific types of equipment and installations, such as data centers, hospitals, and industrial plants. The Electric Power Distribution Handbook provides a comprehensive overview of electric power distribution systems from the substation to the customer's meter. It includes detailed chapters on grounding and bonding, covering the principles and practices used to ensure the safety and reliability of power distribution systems. The handbook addresses the grounding and bonding requirements for various components of the distribution system, such as transformers, switchgear, and underground cables. It also discusses the coordination of grounding and bonding systems with overcurrent protection devices to ensure proper fault clearing. Grounding electrode systems are a critical component of any grounding system. They provide a direct connection to the earth, allowing fault currents to dissipate safely. The NEC specifies the types of grounding electrodes that are permitted, including metal water pipes, ground rods, ground plates, and concrete encased electrodes, also known as UFA grounds. The NEC also specifies the minimum size and installation requirements for these grounding electrodes. Equipment grounding conductors, or EGs, are used to connect the non-current carrying metal parts of equipment to the grounding electrode system. This includes items like metal enclosures, motor frames, and conduit. The EGC provides a low impedance path for fault currents to return to the source, facilitating the rapid operation of overcurrent protection devices. The NEC specifies the size and type of EGC that are required for different types of equipment. Bonding jumpers are used to connect together different metal parts of an electrical system to create an equipotential plane. This prevents voltage differences from developing between different metal components, which could lead to dangerous touch potentials during a fault. Bonding jumpers are typically installed around equipment that is likely to become energized during a fault, such as transformers, switchgear, and motors. Surge protection devices, or SPDs, are used to protect electrical equipment from voltage surges caused by lightning strikes or other transient events. SPD divert the surge current to ground, preventing it from damaging sensitive electronic components. SPD are typically installed at the service entrance of a building and at branch circuit panels to provide comprehensive surge protection. The NEC provides detailed requirements for the installation and use of SPD. In addition to the NEC and the other resources mentioned, there are a number of other standards and guidelines that address grounding and bonding. These include the IEEE Standard 142, also known as the Green Book, which provides recommended practices for grounding and bonding of industrial and commercial power systems. The ANSI/GI-AMINA 607 standard provides requirements for telecommunications bonding and grounding. Proper grounding and bonding are essential for electrical safety. By following the requirements of the NEC and other applicable standards, electricians and electrical engineers can ensure that electrical systems are safe and reliable. There are some common misconceptions about grounding and bonding. One common misconception is that grounding is only necessary for sensitive electronic equipment. In reality, grounding is essential for all electrical equipment, regardless of its sensitivity. Another common misconception is that bonding is only necessary in areas where there is a risk of explosion. In reality, bonding is necessary in all areas where there is metal equipment that could become energized during a fault. A third misconception is that a ground rod is all that is needed for proper grounding. In reality, a ground rod is just one component of a complete grounding system. A complete grounding system also includes a grounding electrode conductor, equipment grounding conductors, and bonding jumpers. When working with electrical systems, it is always important to follow safe work practices. Firstly, always to energize the circuit before working on it. Secondly, use appropriate personal protective equipment, such as gloves and safety glasses. Thirdly, inspect all tools and equipment before use. Fourthly, never work alone. Fifthly, if you are not qualified to work on electrical systems, hire a qualified electrician. Effective grounding and bonding are not merely about adhering to code requirements. They represent a fundamental commitment to safety, protecting individuals and equipment from the potentially devastating consequences of electrical faults. A well-designed and properly installed grounding and bonding system acts as a silent guardian, constantly working to minimize the risk of electrical shock, fire, and equipment damage. Consider a scenario where a fault occurs within a piece of electrical equipment. Without a proper grounding system, the fault current would have no clear path back to the source. This could cause the metal enclosure of the equipment to become energized, creating a dangerous touch potential for anyone who comes into contact with it. However, with a properly installed grounding system, the fault current would immediately flow back to the source through the low impedance grounding path. This would cause the overcurrent protection device to trip quickly, energizing the circuit and preventing any potential harm. Similarly, a well-designed bonding system ensures that all metal parts of an electrical system are at the same electrical potential. This prevents voltage differences from developing between different metal components, which could lead to dangerous touch potentials during a fault. For instance, if a metal conduit is not properly bonded to the equipment enclosure, a voltage difference could develop between the two. If someone were to touch both the conduit and the enclosure at the same time, they could receive an electrical shock. Grounding and bonding also play a critical role in protecting sensitive electronic equipment from damage caused by voltage surges. Voltage surges can be caused by lightning strikes, power grid switching, or other transient events. These surges can damage or destroy electronic components, leading to costly repairs and downtime. A properly installed grounding and bonding system provides a low impedance path for surge currents to flow to ground, diverting them away from sensitive equipment. This helps to protect the equipment from damage and ensures its continued operation. In conclusion, grounding and bonding are essential for electrical safety and equipment protection. By understanding the principles behind these practices and following the requirements of the NEC and other applicable standards, electricians and electrical engineers can create safe and reliable electrical systems. Remember that grounding and bonding are not just about meeting code requirements, they are about protecting people and property from the hazards of electricity. By taking the time to properly design and install grounding and bonding systems, you can make a significant contribution to electrical safety.